Hey, Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!
Hey, how's everyone doing? Good to see you here. Kayla, good to see you here. Jesse, Michael in the chat, Gia in the chat, Sierra in the chat. Good to see everyone here. The lighting seems different. I don't know. Am I turning red? I don't even know anymore. Oh, what's going on? What's going on? Well, I want to go look in the mirror. Hey, sup? Good to see you here, Sam. We got the Kahoot in the background. I feel like something is off. Let me go fix this. Something weird in the neighborhood. I think it's as now you see it sounds crazy. I have no idea what's going on. Beats. Thank you right there, Sam and Emma. Good to see you. James, good to see you here. We're gonna get started on Kahoot here in a moment. Can't wait for this review. Chelsea, so good to see you here. Thank you so much. Let's boot up Mewbot. Mewbot's gonna crash the world around us. It's just we got done with classes today. Your glasses are turning. Kayla has one of our famous quotes from the Kahoot. Kayla knows what quote number it is. But so good to see everyone here. We got the Kahoot playing. We already got Mountain Gator. We got Dynamic Orcs in the chat. That's how you say that word. What's up, Chase? Great to see you here. So many people joining in. Might even send out a message on, is there a class on Tuesday, Thursday? You bet there's class. We will have class. And we're going to play some Kahoot here and do some review. We'll have class all this week. Rare instances when we cancel class. Let's pull up the, I'm going to drop it in the Discord right here. Discord helping out. Loads. Oh, it should make the file. Oh, so we'll respond to that in a second right here. Yep. Still have class. Yep. Still have class. I can meet later and double check and make sure it is created. It should create the file on your computer for you. And we'll drop this and we'll tag everyone in 320. Kahoot live. Okay, there we go. Currently live. Am I just gonna have to watch the Kahoot Friday? I guess you might have to. Sam, sorry about that. You can join in. You can play. Kristen, so good to see you. Giving a shot right here. Well, we got some people. So you never know, Kristen. You got a shot at this. And if you take 320, we'll get started here in 2 minutes. So that way we stay here on the screen for 2 more minutes. Wise Owl for the win. But we got Smiling Ostrich and Clever Pony. Clever Pony. Don't get some what is it? What do ponies get hit by? I can't think of the name of it. Oh no. Silly Fox, you're my favorite right now. Silly Fox is gonna win. We got Silly Fox and Polite Shark right here. Clever Pony, Wise Owl, Blue Puffin, Radiant Sphinx, Epic. Gotta say it like this though. You gotta be like
Epic.
Epic Buffalo, Agent Fox. I like that right there. Let's see who's gonna win. Flying Bee is such a redundant name. Did someone seriously get Flying Bee? So you might restart and get like another thing. I'm drinking the Waterloo. Are these from HEB? Waterloo Blackberry Lemonade, sparkling water. Probably a product of HEB. Hole 3. Check it out. Epic Speedruns. Oh, yeah, from the Epic Speedruns, the
Epic Speedruns.
Just a little bit of time left. Okay, sorry. Space Sloth. Okay, that might be one of the coolest names. Space Sloth. Really great name right there. Shining Otter, but I think Space Sloth. You got the best name right there. You're already winning on name alone. Who got Space Sloth, if you want to say in the chat? Fuzzy Bat. Did someone wait? Did we lose the... No, we're still Flying Bee. I like that Flying Bee is so redundant. That's like, Flying Bee? Fuzzy Bat's cool. We got seconds to go right here. 18 seconds. Might try to wait till we get 20 people again, then we'll start. We just lost some people. Why'd we lose people? What happened? seconds to go. So make sure who's ready in the chat. We need some I'm readies because we're going to be playing here in just a moment. We're going to be doing a review. We're going to do $30 first prize. And we're doing, I guess I'll put it in order. $20 second prize. These are Amazon gift cards or Starbucks. And $10 third prize. Amazon gift cards or Starbucks. Pin messages right there. SpongeBob's ready. I'm ready's in the chat. There we go with the message pin. I'm ready's to go. You get the gift card. I sent it to you. You just tell me your email if you win. First, second, third. Tell me if you win. Make sure to let me know. Email me. And yeah. Oh, you did? Kayla, if you can just tell me, send it to me. Let me know. Did you forget to email me or something? Let me know. Like, I'll make sure, like, and you forgot to claim it. No. Well, email me and say, Brian, I'll trust you that you won last semester. Try to figure out how much it was again, and I'll just send it to you. So I have the screenshot still. I trust you. I don't think you're gonna try to be like, oh, I've won 10 cahoots, Brian. I'd be like, then I'd want screenshots if you told me you won 10 cahoots. With that, it is time to Kahoot. Let's do this. Here we go with the first question. Tons of teaching to the test moments coming up right here. First question is going to be, state your conclusion regarding the QQ plot. So we need to know what a QQ plot is and what a QQ plot is telling to us about. A QQ plot is going to look at what thing? Who can help in the chat? We're doing a review right here. I said $500. I want a video of that. QQ plots help us analyze what? This is a 201 question also. What are we going to look at in a QQ plot right here? Who knows what QQ plots are going to help us look at? I'm not blocking a right answer. QQ plots are going to look at normality. Ooh, we did pretty good. We tricked some people right here. So whenever we see a QQ plot, you usually see this in the output on below it where it says if it's normal. So when would we decide, and this is a good review because a lot of misses on this. That's what we want to see. That means we're hitting upon areas we need to review. When does a QQ plot show normality? And let's bring up R right here to help out. When does a QQ plot show normality? Like when would a QQ plot look normal? Like if I go here and store some data and do random normal data and do like 100 points and I look at a QQ plot of it. So when would a QQ plot look normal and what does it look like? Don't worry. Good practice. You got the normality part of it. And when does a QQ plot look normal versus when does a QQ plot look not normal? These are exponential numbers created from an exponential distribution. So if you had a histogram, which we don't look at the histogram, if you had a histogram that's mostly normal, the QQ plot will follow the straight line, which is just plotting the z-scores of what we see on the normal versus the observed value. So it makes this line right here where they match. That's why the red line is like a 1 to 1, 0 to 0, 1 to 1, or negative 1 to 1, negative 2 to 2. So the red line is when the values match what we would expect. But when you have a distribution that's not normal, i.e. a skewed distribution, then we are seeing things that don't follow the red line, where we have the values that where they would be if they are normal are way off. Like we are observing values way off the normal curve, and that's what we see over here. Great job right there, Emma and Sierra. And we got to throw out 100 points, so keep the answers coming in. Make sure you take these notes like QQ plots or normal quantile plots, gauge normality by looking at if the data goes along the red line, meaning it's normal, or if data doesn't go along the red line, meaning it's not normal. And so this one mostly follows the red line. Mostly. Those dashed lines are kind of like, you're like, lines. What would you say right here? Now there's no exactness to this, but when would you start to doubt its normality? Like who can maybe give a lot of people like fine lines in statistics, but that's not what we do. But what would you say as like if you're looking for like it's probably not normal if this, like at what point would you say? Outliers will yeah, exactly. Things that are far away. Great job, Gia, right there. Things that are far. So we want to see really, that's Kayla's pointing out right there, points that are outside the dashed red lines. We want to see more points outside, and there's not really any there. But if you look at the example we have here, at this point, it's like, no. Does everyone see how it's very clear down here on the bottom side that there's such a deviation from the red line and the dashed red lines? There's issues here. That's small issues. That's small. But this is no. You look at that and they're like, no, that's not good. That is way outside of what we would expect. if you look at this and you're like, oh, like here, watch this. If you had, in this instance, oh, I did the core demo. Nope. If you had this 1 point right here, would you conclude that this is normal or not normal? Last question on this one. Normal or not normal? You have 1 point right here that's not within the kind of line. There's 1 point that's not within the meh. What's your thoughts on it? I'd say it's normal. You know what's the thing? I actually made it from normal data, so this is actually normal. It's like, you see that and someone's like, that's outside, and you're like, eh. It's the best way to describe it statistically is like, it's good. It's good as Michael's saying right there. It's fine. It's not that bad. It's not like the last one we were seeing where it looks all kind of crazy like, and it's like this is ridiculous. This is not normal at all. That's way outside of the bounds of normality. So a QQ plot or normal quantile plot lets us gauge if the data, the univariate quantitative data, comes from the normal distribution. Who's in the lead? Dynamic Orcs is in the lead. I think that's how you say it. But Flying Bee, redundant name, but redundant name is winning. And Blue Puffin, Jolly Owl, and Shining Otter. Can you keep the winning up with the next question? Here we go. Compute the expected value. Ooh, this is tough. Who has their calculator out? Someone's running or quickly clicking calculator on their computer. Quickly clicking calculator on their computer. Quickly click calculator computer. Some good practice coming up here on expected cell counts. Ooh, only a few people. Click an answer. If you don't have one, click an answer. Take a guess. I don't think you get penalized for taking guesses. Okay, only a few people got it. Who here knows how to find an expected cell count? So don't worry if you got it wrong, or don't worry if you didn't get an answer. And this is going to be a close game. There's going to be lots of points and lots of practice. This is an older question, but who knows how to get the expected cell count? Who knows how we would get it? Like, who understands the formula? I'm going to show you it here visually to help remind us. And remember, you get a cheat sheet, so your cheat sheet can be a huge help for this. So this is one of those things you'll be like, oh, I need to put this on my cheat sheet. So are you ready? Who knows the formula? Anyone in the chat, help me out with the formula. And I'm going to show you the formula here. Oh, nice job right there. Row total times column total over grand total. Great job, Jesse. Let's throw out some points for that. Jesse, great work. Row total times column total over grand total. And I think Ella is also showing it right there. This one says Verizon rarely. So we're looking at the combination of rarely and Verizon. So what you need to do is you need to circle those numbers like this. And those two numbers get multiplied, and then you divide by the grand total. So this is what I call a grand total right here, or like the sum of everything. And then it's divided on the numerator is the row total and the column total. And those do not matter if you reverse them. But Ella, great job. Ella, wow, we only had a few people get it right. But write this down. Put it on your cheat sheet. This is a cheat sheet thing that you don't have to memorize. It's a classic formula. It's how we get the expected counts. Row total times column total over grand total. Make sure you understand it. Like seeing it visually here might help, that you just go to whatever row it was, or rows are this way rather. Even I got to practice. Rows are this way. You go to the row total for that respective thing, like Verizon, row total right there. Go to the rarely column total right there and divide it all by the grand total after multiplying the two. Can anyone here with some practice, we like to practice, tell me the expected cell count for, and it's probably better if I view it this way, who knows the expected cell count for often AT&T? So if you get good at this, you can solve any instantaneously. Often AT&T. Find me the expected cell count. This is like how many we would expect for often AT&T, and I'm not blocking anything right here. There we go. No, I'm not. So often AT&T would be what? And you can show me the mathematics, or you can solve the number. And this is good practice. Like, okay, find the expected cell count of this. It might be 11. It might be. Let's find out. Good answers. I'm not going to color code it so much this time, but there's that, multiply, there's that, there's the equation. I'm going to take everyone's word for it. That's 11.1 or so, and just probably carry all the decimals on the test just to make sure. If you think something counted you wrong, let us know, and we can always check. But there it is right there. Do you see how if we circle the numbers, it makes it nice and easy to just do it right there? And great job right there, Sam and everybody, and Emma and Thomas. Great practice. Row total times column total over grand total to find the expected. And that is how many we would expect by random chance, given there's no relationship between X and Y. So good practice right there. Who's in the lead? We're going to find out. Flying bee, no. Well, you can't. Ooh. Only 2 people on the leaderboard got that right. Let me say this. You do not get penalized for guessing. So take a guess if time is running out. You got a 1 in 4 chance of getting it right. Maybe a lot of people on the top guessed. Maybe Wise Owl guessed. You don't know. Well, don't worry. There's a lot of room to win and a lot of practice to come with the next question. Here we go. True or false? Side-by-side box plots compare a categorical Y and a quantitative X. Side-by-side box plots compare a categorical Y and a quantitative X. Side-by-side box plots. I try to ask every hard question I can ask on here. I try to make the Kahoot almost harder than the test. But I'd write down all of these right here. I'd understand them, especially QQ plots. What is the issue with this? What is the issue? Gosh, I feel like I'm mean tonight. What is the issue? Who understands the issue with this? When we talk about side-by-side box plots, and let's look at some of that output here, because these are like the older topics we haven't seen in a long time. James is right, they're flipped. So box plots are quantitative, and that's the Y variable of interest. So we're going to load up some data right here. If you're getting question wrongs, please stay. Like that means stay, hang out, ask those questions, practice right here. It's a categorical X and a quantitative Y exactly. So when we go to the associate function, this is output we need to know how to read and understand right here. We're going to load in data from survey 10. I mean, is there any other survey? No, there's not. And we're going to look at the heights of individuals with their gender, and we'll go here to data, survey 10. Let's look at handedness. This one we won't see, handedness. Okay. So here's the heights of individuals based on their handedness. Now, let me ask you, do you think I should compare means or medians? This is a good test question. We're in one of those teaching to the test moments. Do you think I should compare means or medians for this data? Should I compare means or medians? And we have the side-by-side box plots with a categorical X and quantitative Y. Should I compare means or medians? I'm being a little forgiving with the one I choose and why. So other than means or medians, I would need to know why. Should I compare means or medians for these groups? What do you think? Means or medians? We've got a split between the class. So which should it be and why? Go into more detail. I need some more detail on this. I see what people are getting at. What are you looking at to compare means or medians? What is helping you decide? And hence why I'm off the screen. What is helping you decide if you should use means or medians? What is helping you decide right now to pick between means or medians? The QQ plots. Exactly. This is helping you decide. And if you chose medians, I would give you it only if you told me one thing. So where could you make that decision with this graphic? I'm going to make it so the plots a little bit. Where could you justify that decision for me? The decision to use medians could only be justified where on this? Like usually we've had this as a written response and I can't appear. That's what I think, Jesse. I'm going that way on it. I go with Jesse on this. 100 points, Jesse, right there. That's my answer. And so for people saying medians, what do you need to justify it with? So to compare medians, we need evidence of non-normality. And where are you looking? Oh, I might answer in a second right here. Jesse, you got it. Jesse, just on fire. Jesse, I want to throw... Jesse, you're seeing what I'm seeing, and I'll point to it and I'll explain it. Jesse, 500 points. Jesse, great answer. That's why I can't block it. This right here. Don't look at these. These are not the normality plots. This right here is where I see a little bit of a break in the normality. It's because of this area of data. Don't look at the histogram. But the QQ plot has a problem down here. These are mostly normal. That's mostly normal. I know it's got some weirdness down here, but it's a small data set for the ambidextrous individuals. But if you went and said this is some non-normality, you would compare medians. If you say not a big deal, you compare means. That's the subjectivity to statistics. And so if we compare medians, here's the thing though, Rock knows. It doesn't matter. Because means versus medians, both of those differences are what right here? Means versus medians, both of those differences are what? Means versus medians. There's the means and there's the medians. Both of the differences in the heights of individuals, whether they're left-handed, right-handed, ambidextrous, both of these differences are what? Like if we say, let's compare the means and see if there's differences in the means. they're not statistically significant. There's no big difference. We did all this, like, what do we compare to find out, hey, there's no difference here and there's no difference here, nothing going on. Now tell me, are you confident in your conclusion? Another good test question right here. We're covering lots of test questions. Are you confident in your conclusion that it is not statistically significant, yes or no? You have to know how to read the output right here and be able to tell me, are you confident in your conclusion that these are not statistically significant? How would you tell me about that? What would you use in this output to be like, you are confident that they're not, that they are conclusive, or you're confident they're not conclusive? What would you tell me about the conclusivity of these tests? Pretty much, John, exactly. John's answer right there. When we are looking at intervals for p-values, the important value to look for is 0.05, Sierra perfect answer right there. We are looking to see if 0.05 is in the range, because 0.05 is when we go from not significant to significant when we go below 0.05. So because 0.05 is not in the range, we would say, well, we have evidence that they're not statistically significant, and we're pretty sure about that conclusion. Exactly the interval. Great job right there, Thomas, and really good review, because we haven't seen this output in a while. So this is a great review, and these are the means for the groups, and these are the sample sizes for the groups. So great practice. Who's in the lead? Oh, this is a whole shakeup of a leaderboard. So you could win. Dynamic Orcs is leading the way, but who knows? Next question. Let's try it out. True or false? Scatterplots contain a quantitative y and a quantitative x. Space sloths, let's go. I saw some quick answers right here as Kahoot thinks about the graphic. Well, that's weird. That's never happened. Oh, please let there be good answers on this. 201, are you still here? If you're still here, what do you think in your head when you hear this right here? What is instantaneously in your head right now? Who has any sort of saying as the graphic just doesn't work? They must have removed it from their library. Good to be here, Sam. What do you think when you hear this? And I'm happy with that result. That's worth another 100 points as I go to pivot review. It kicked you out. Oh no, join back in. I've got the code right here. I'm sorry if you lost your points. QQ straight enough. No outliers. So when you talk about scatter plots right here, as Braden says right there for 100 points, QQ straight enough, no outliers is two quantitative variables. So a scatter plot is when we do two quantitative variables right here, and we could just switch the variable type. And that's what's great about the associate function, is now we get a scatter plot. And probably the biggest issue right here, and this brings up some conversation, probably the biggest issue is going to be what with this scatter plot. So Kristen, great job and great practice. What do you see issues with this scatter plot right here? I think the biggest issue with this scatter plot is what? What is the biggest issue with this scatter plot? The biggest issue with this scatter plot is probably it's outliers. I think there's some outliers. Ooh, but also, think about this right here. You see what else am I trying to tell you about? What else? It's a good review for 201 also. What else am I trying to tell you about? I'm like, yeah, I see this and I see that. It's curved. I don't know if there's thickening. There might be. I'm seeing outliers. I'm seeing non-linear. I'm seeing things like this. So this is a concept 201. You won't know 100 points right here. 201, so glad to have you here, because now we're into a concept that'll be new for you. There are problems with this, but it's like your favorite band, and you're happy it's like your favorite band. What's your favorite band right here? Monotonic, but what's your favorite band? Which means we can do something with this because it is monotonic. What's your favorite band? Hence, this goes in what? What does this data go in right now? Because it's monotonic, one direction, best band ever. We all know that. So it's one direction, it goes in, and that means it goes consistently like up, or it could go down. And this means we could probably use what to describe it. What could we use to describe this data instead of Pearson correlation? It's on the screen. Instead of Pearson correlation, what could we use to describe this data? Instead of Pearson, Kristen right there, big fan of One Direction. Spearman. So basically, Spearman is rank correlation. It says it right over there. And rank correlation downweights outliers, deals with heteroscedasticity, and deals with nonlinearity. The number one thing for Spearman is the data must be what? So don't tell me your favorite band this time, but the data must be what? Which means your favorite band. The number one thing for Spearman is the data must do this sort of relationship. It can't do this. No. It can't do this. It must be monotonic. So the data must be monotonic. We'll talk more about some heteroscedasticity later. It must be monotonic. And does everyone notice right here that the Spearman's picking up on it a little bit better? And of course, we have a scatter plot with 2 quantitative variables. So good stuff right here. Great work. Who's in the lead? This is a close game. Epic Buffalo. Got some epic wins coming. You're going to win, Epic Buffalo. I know it. I got my... it sounds like something you order at Buffalo Wild Wings. I'll have the Epic Buffalo. I'd order it. Next question coming up. Here we go. True or false, histograms display a categorical variable. Now, the answer was actually on the previous slide. Well, that kind of gives it away. Histograms display a categorical variable. True or false? So we've been talking about this a little bit. We're going to go some tougher questions here in a moment. I hope. I got Mewbucks on the Epic Buffalo. If only we could vote on it and bet on it. That'd be pretty fun. We'd be allowed to do that, right? I think. I don't know. So 500 Mewbucks. Oh no! Histograms. Because let's go back here to the data. When we look at a histogram, what do you notice is on the side of this scatter plot? The scatter plot has what on the sides of it? What are these? What are those? Oh God. What are these on the side of the scatter plot? I see 2 whats? The scatter plot. Oh, don't worry, it's just practice. It's just practice. Histograms are for what kind of data? Remember I turned this into a histogram? Yeah, that's a... One time was said during a Kahoot. 2 quantitative variables. So histograms display quantitative data. Now, you might be thinking of, which Jump does not help with the ambiguity of the terms right here. Jump will call this a histogram for number of pets, and then it drives me absolutely crazy that Jump will say that, like, born in Tennessee, it'll put on this histogram. It'll have histogram options. They should put bar chart option, but that often confuses students. This is a bar chart, and a bar chart is when you use categorical data. No, don't worry. There we go. Bar charts are below, and that's a histogram up above. So this is a histogram because it's quantitative, and this is a bar chart down below here because it's categorical. Oh, you got it. Don't worry. This is, and like write things on your cheat sheet if you want. We're going to look at more output. That's what we're going to try to do, is like cover as much output as we can, analyze as much data as we can. We're just here to practice. Like, let's pull up another survey. Let's do one more survey data question right here. Remember, we're here to practice. We're going to see who wins, but it's all about that practice. What am I doing? Library. We're going to survey 11 for once. You know what? There's actually an attractive survey. Like, what are people attracted to? Should we see who females are attracted to or who males are attracted to? Take your vote right now in the chat. We're going to ask for females or males. We only have the 2 data sets right here. But that's what was collected right here. So we're going to look at the female attraction data set or the male attraction data set. So Kristen's voting males right there. And so they were asked these questions right here. So we have these data sets, and let's take a look. We'll see. I'm going to go pretty quickly on the vote. Females is winning 100%. 100% already? May only have 1 vote in there. Males, Thomas says. So right here to data. People voted 100% female vote, but people are saying male in the chat. Female is still winning, so attract female right there. Okay. 75% of the votes in. Watch it change right as I end the poll. So we're looking at females, and you can take a look at what the data sets are by doing the question marks on them. The average attractiveness score of 70 females along with physical attributes. So it's their attractiveness score. Data from 70 observation of the following 21 variables. So all these different things were collected on these individuals. And we have all this information right here, all this interesting stuff. So let's look at their attractiveness score. And we could look at something like so many things. If they're wearing glasses, cool. Score, because I got to know, glasses. So we're asking the big questions today of, does a female's rating of attractiveness depend on if they're wearing glasses? Oh my gosh. Well, I think we have that for the male data set too. Well, I did not expect this. Turning into Cosmo. What did we see right here? Remember, this is real data right here. What do you notice? And wow. Owen Wilson.
Wow.
What do you notice right here with this data immediately? Remember, we do have histograms, quantitative data. We do have box plots, quantitative data broken apart to different groups. And what should we compare? Let me ask you a big question. Should we compare means or medians with this group? Should we compare the means or the medians with this group? What do you think? Means or medians? I know it's crazy. I'm like, what is going on? I would go means for this most definitely. Definitely means, because the data, if you look at the QQ plots here, it's pretty normal. That is, and I'm one who's had 2 eye surgeries. So I'm guessing, how do the males fare on this? We might be able to change it because I think the data is the same for males are collected. What? Oh, no, it's still the same. Wait, was it no and yes? Did they switch spots? Oh, it's no and yes? Well, that makes it confusing. The males actually don't have a statistically significant relationship right here for the male output. The females did have a statistically significant relationship. And are you certain of that? If you compare the means between the groups, there is a statistically significant relationship. Are you certain of that? Are you certain of this? Would you say you're pretty certain that there's a statistically significant relationship here? Yes or no? What would you say with that output right there? That there appears, would you say you're pretty certain of it? Because 0.05 is not in the range. The whole interval for the calculation of statistical significance is below 0.05. So yeah, a little social psych right here. And for males, why are you not certain about the male? We're kind of hammering home this topic right here, making sure we know it. For the male data, we see that it is not statistically significant, but I would say I am not certain about this conclusion. So the male data is not statistically significant, but I'm not certain about this conclusion. And John put it correctly right there. So do remember, when we do p-value intervals, we're looking to see if 0.05 is in the interval. So for males, we did have not significant, but we're not certain about the conclusion. For females, we had significant, but we are certain about the conclusion, because 0.05 is not in their interval. Wait, what do we say? If it's in the interval, it's inconclusive. Someone said that this semester, that if 0.05 is in the interval, then the test is inconclusive. And that's only for p-value intervals. That's only for p-value intervals, not for slope, not for intercept. Those are different concepts with different intervals doing different estimates. But the test is inconclusive when 0.05 is in the p-value interval. So when you wear glasses, pretty crazy, right? So I don't know. It's pretty interesting. It'd be fun to do like a full, like, you can check out these other data sets if you want. Some pretty fun analysis right there, I think, to just look through and see what people said. Whew, Epic Buffalo, you got this. But Melodic Mouse, who knows? And Blue Puffin and Polite Shark. Polite Shark, you can do it. You can win, Polite Shark. Don't be polite, just win. Next question, here we go. Quiz question. What is the best way to investigate normality? You should know by now. Number one way to investigate normality, whenever you're trying to see if things are normal, is to do what? Number one thing when looking for normality is, you should know, we've practiced this a lot. Don't look at the those. Great job.
Wow.
Oh, that was the wrong wow. There we go. QQ plots for normality. And how do you know that they're normal? How do you know these QQ plots for normality are pretty normal? Which those appear to be. We're talking about these graphics. How do you know that they're pretty normal? You're like, yeah, it's pretty normal. How do you know those are pretty normal? Like, yeah, it's pretty good. Talking about these plots. These are the QQ plots for normality. No. I think glasses. Chelsea now wear glasses, so I'm pro glasses. Put me down as pro glasses. Those people don't know what they're talking about. Look at the QQ plots right there. Pro glasses. I want to see some, like, glasses are awesome in the chat. I should go, you know what I should do? Maybe we should take a 1 minute break and I'll do a stream of my glasses. I'll go, what should I do? Should we do like a 1 minute break and Brian go put on his glasses? We'll do that yes or in a moment. But I'll go pro glasses right here. Blind people. I've had 2 eye surgeries, so we love glasses right there. All about it right there. So yes, do it. Maybe I'll do it at the end here. We'll do it at the end maybe. That way we can keep the review going and we'll do it here. We'll have glasses Brian visit the stream. I don't think I've ever streamed in my glasses. I put them on at night to give my eyes a rest. But I've had 2 eye surgeries, so whew. Not the fun eye surgeries either. I know. We'll do it right here. You got it. And here we go. Dynamic Orcs in the lead. Epic Buffalo. Great job right there. Continuing on. Next question. If the relation between 2 variables is monotonic and linear, which option should you pick? Now, that's all you know. It is monotonic and linear. This is all you know at the moment. So don't go outside of what it says. Well, I wear contacts during the day. think of 201. And when do we use Pearson? When do we use... I had to search it at 2 and 12. So we were split between Spearman and Pearson. Now, I think the reason we were split is because of a word in here that had people think Spearman would be the option. What word did you see? If you said Spearman, you're like, but it says this. It says this. So if you pick Spearman, monotonic, right? But tell me this. Every line must do what? Finish my sentence. Every line has to do this. If it's a line, if it is a line, if things are linear, every line must do this. Every line must do this. Every line must do this. Every line has to do this. If it's a line, it will do this. Every line has to go in one direction. Exactly. And Spearman is more often used for not linear. So if I said not linear up there, then they'd be like, yeah, Spearman. Then that's really good. We don't have the linearity of Pearson. And so Pearson is your classic Stat 201 QQ, straight enough, no outliers. So we didn't mention anything about outliers here, and plot doesn't thicken, but all lines go in one direction. So being linear, it has to be monotonic. So kind of a trick right there. I know, a little tricky right there, but the big thing that you want with Pearson is the data to be what? Like if you're using Pearson, you definitely want it to be this. So if you're using Pearson, the data needs to be this. Like I'll pull up, we were doing some work today on the homework assignment. Check out office hours today, some office hours, and swing by office hours anytime when you're working on stuff. If you are doing Pearson, you want your data to be this. Now you might say there's little problems here. You want it to be linear. So you must have the linearity to do Pearson or to do linear regression, which this is a linear regression, but we could still do like Pearson. Now you could argue, and we could look at this, you could argue that maybe we should use Spearman, but your argument for Spearman would be based on what? If you argue for Spearman, you might be arguing based on what on this? If you argued for Spearman, you'd probably find to use Pearson here. Monotonic means one direction. Good question, John, right there. It means it goes in one direction. Like this goes up. It doesn't change to go down. Like something that's non-monotonic would bend. It would have some sort of change in direction. So this is monotonic because it goes constantly up. Good question, John. 100 points. Thank you for asking. You could say a little bit of outliers or a little bit of heteroscedastic. I don't think it's strong enough, and we shouldn't do this, but we could look. Notice how these are virtually identical. I think you're fine to use Pearson. And you'll see that a lot of times that the Pearson and Spearman will be very close if there's no discernible difference, where, there's not a big difference in spread. There's not a large amount of outliers. That's about as good as you see when it comes to data, like surprisingly good. So for the most part, I think a Pearson relationship or a linear relationship would be pretty good for this. But yeah, so does that make sense? When we use Pearson, the number one thing to know about Pearson is that it is a what relationship? The number one thing to know about Pearson is a what? So let's write this down. This is a really great review right here. When using Pearson, it must be linear. That is number one on the list of what it must be. And then problems are things like, what are problems? Let's list all of our problems right here. The problems would be things like what? Mary, great answers right there. Mary, 100 points. Problems would be things like what? So problems would be, we could just go for the easy low-hanging fruit right here. We're going to have problems if it was what? So what are going to be some problems? Like things we don't like. Like, we don't want that with our thickness. So heteroscedasticity or thickness change. Thick. See, I can't spell the easy word. We have problems with nonlinear. Yep, if it's nonlinear, that's a problem. And then outliers. And then last but not, so QQ straight enough. No outliers, plot doesn't think it. Is that everything? I think we did it. QQ straight enough and outliers, plot doesn't think it. I'm like reviewed it in my head. And then what we could do is then use Spearman, but with Spearman must be monotonic. So this is kind of your order of operations. Does this make sense? We've kind of right there, Kristen. 100 points, Chris. Greg, we have the chat. This is kind of your step-by-step. Like you usually go for Pearson because you're just using the variables as is with a linear relationship. Then you're like, okay, wait, it's got thickness problems. Like it's changing in the thickness of the plot. So if we see something where it's heteroscedastic, like the plot's getting thinner, then we'd say, okay, that's a problem. If we see it has a non-linear relationship, that's good. Now, why are we in double trouble on this one? Why is this one like, nope, nope. Why is that non-linear really bad? Why are we like, well, we're not going to be using the techniques of Spearman on that. We do have ways of handling it with a polynomial model, but why would we be like, nope, not using that. It's not monotonic. It's non-monotonic. It goes, and to John's question earlier, this goes in two directions. It goes up and then it goes down. And that's what we mean by non-monotonic. So you could have something with outliers, and outliers drastically impact. So Kristen, we were talking about this today, that outliers drastically impact, but then we have a way of handling this. Someone said, well, don't do Pearson correlation to this, use Spearman. So we have ways of handling this to be like, oh, there's outliers, well then let's use Spearman, but it still must be monotonic. What do we say if we have data like this? We say we can't handle it. That's like, well, we don't have a good technique right now, but there are techniques, so we will be talking about that later. Okay, great job and good review. Let's use in the lead. Wise Owl and Jolly Owl. The owls are coming. The owls are coming. Take me away. What is the lowest possible p-value? Oh, that's an easy question. We got this. What is the lowest possible p-value? Oh, please. Oh, please. Oh, please. P-values range between what and what? What is the lowest possible p-value? It technically would be a limit because anything is possible. If we observe it, it has to occur. So what is the lowest possible? Exactly. 0. 0 is the lowest possible. Correlation goes as low as -1. Statistical significance is found at 0.05. Oh, please. Oh, please. I'll take it. I think that's a pretty good result right there. So the lowest possible p-value is 0, telling us that what we saw was basically what? Like, let's try to interpret a p-value by saying that the relationship these two variables have right here by random chance would be basically what? Like, I'm looking at this data and being like, Brandon, so good to see you here. We've got 2 2-or-1ers here. That's worth, why not? Let's throw out 1,000 points for our 2 2-or-1ers here. Both Kristen and Brandon here. But so good to see you. What does this p-value mean to us? That what I'm seeing here between these two variables is virtually what? And it is the likelihood by random chance, but that p-value is basically 0. It's telling me that what I saw here is virtually what by random chance. It's telling me that what I am observing is virtually, think about 0. If I tell you the probability of this occurring is 0, I'm telling you that this result is basically what by random chance. Ubot cracking up about some randomness. I'm telling you that the results right there by random chance are virtually what? The results by random chance are virtually what? No, well, it was very unlikely by random chance. Oh, yeah, I agree with that, right, Jesse? I do agree. Jesse, let me throw 100 points for disagreeing improperly. Jesse's saying it doesn't look to be random, like super improbable. Basically impossible. Davis, the exact answer I was looking for. It's like, this would not occur by random chance. What would occur by random chance is actually, when we think about like a residual plot, look at this right here. The correlation values are closer to what for plots that are likely by random chance. A correlation that is likely by random chance would be one that's just between two random relationships. And what would a correlation likely by random chance look like? Yep. Oh, great job. That's Kayla, great mnemonics in the chat. Kayla dropping some mnemonics, or always remember. What do you think the correlation is close to for this graphic? The correlation for this graphic, which I created via randomness, and so this one is by random chance. Like, it's literally by random chance. So the correlation to the p-value, Brendan, might be reversing the two. The p-value is going to be closer to 1, which I know that's not 1. If I keep rerunning it, we will see maybe a high p-value. So the p-values here are going to be higher, and there's a high p-value, and the correlations are going to be closer to 0. So all of these correlations right here are by random chance. Like, these are literally being created from the code rnorm, which is random normal numbers. And so these are random numbers. There's no relationship between random numbers and random numbers. And so no worries, Brendan. 100 points again. Don't worry. Good practice. And so the lowest possible p-value is 0. But here's the thing. You could keep running this, and by random chance, you will eventually find something statistically significant 1 in 20 times. So we've done it about 20 times. Each one, not like we're more likely to find it on the next one. It's just a 1 in 20 chance every time. Come on, lottery. Man, it's not our day today to win the random lottery. We'll do it 10 more times. It's like a video. Oh, we got it. There we go. So you might look at this result right here and be like, whoa, statistically significant results. Even though this was unlikely by random chance and we got a correlation of negative 0.24, this would happen about 1 out of 100 times, and it did happen by random chance. Now, I had to generate a bunch of random results right here, but the p-value tells us the probability of getting this or result more extreme by random chance. And yeah, one last thing to mention right here is we have what's called the permutation procedure. What does the permutation procedure do to your x and your y? So if you were to take, this is the last thing, we're talking about the permutation procedure. Who here thinks they know the permutation procedure 100%? Does anyone I understand completely what it means to permutate the x and the y and look at the random chance of them? Does anyone? We'll take a look right here as I talk about this. Let's take people's heights and let's take people's weights. If I permutate your height and your weight, it means you walk up to me and you say, I am 5'10". And I say, okay, you now weigh 200 pounds. You say, why? And I say, randomness. I would just choose a random weight for you to be. Your height and your weight would have a what relationship now? If I assign you a random, oh, we got this. We're going to break spring break-itis right here. If I assign you a random weight, then your height and your weight would have what relationship? If you walk up to me and say, hi, Brian, I'm 5'8", and I say, okay, you're 210. And you say, hi, Brian, I'm 6'3", and I say, okay, you're 110 pounds. Or you say, I'm 6 feet, and I say, you're 180. And you say, oh, that's good. And I say, oh, just randomness. If you like it, there's no reason. So your X and your Y now, by permutating them, which I'm doing up above with the code, have what sort of relationship? So your X and your Y have what sort of relationship right here? What kind of relationship do X and Y have if they've been permutated with each other? Permutating means we just choose a random X with a random Y, and we just say, you're together, and you're together. What kind of relationship would they have? A completely random. They have no relationship. It's just random. There's none. There's no reason. When it comes down to people's heights and weights, there is a relationship. Does it make sense to say there is a relationship if we try to understand what height someone is with what weight somebody is? So we take someone's height, we take someone's weight. There is a relationship between height and weight. People who weigh more are generally taller. There are outliers, but there is a general, somewhat linear, non-linear towards the end, relationship between height and weight. But if I were to take and do random heights with random weights, what would you see right here? Now, we actually got something halfway decent. I'm shocked. Let me do it again. I guess it's pretty random. Everyone here is a random permutation. Does this make sense that everything you're seeing here is random permutations? Who's following me? This is how permutations are created, is that we're literally just taking a random height of a person and a random weight and then putting it together and saying, here's your height-weight combo. And now everything you see right here is random. Compare this to our graphic where you actually see some sort of relationship in our graphic. Here's the random graphic behind me now. And here's our graphic. Our graphic actually has a relationship unlikely by random chance, and that's the p-value. Permutations often have correlations closer to 0, and there's the correlation close to 0, and also a high p-value. So what's the point of using permutations? The point of using permutations is it actually helps us calculate a p-value. This is a very new school of statistics, Ella. Great question. This is not using classical methods of finding the t or the z or the chi-squared. We're actually simulating random chance because each permutation shows us what would happen by random chance. So what we would have to do, watch this, really quick on this, is we would actually have to create a correlation test between y and x. I don't do that so often. We take the value of correlation. And so what is it? Let me store it as a list. So let me store core as a list. What's it stored in as here? And is it the statistic? There it is. No, that's the t statistic. I want the t. I want the estimate of the correlation. There we go. And let's do this as numeric. And this is good practice, especially for 474. I don't want to scare anybody. And here's what I would do. Who knows what I'm going to do next right here to run 500 permutations of correlations by random chance. So what would we do right here to get 500 random chance? Would I just keep running my code? like this right here and just keep doing this and get different correlations. Like, look how they're all close to 0. These are all the correlations I'm creating by random chance down here. So what would I do to run my code 500 times? Who has an idea? We would run a for loop right here. And with the for loop, we could store in the values of correlation. And then we can literally create variable is I in vector 1 through 500. And we could create 500 values right here of correlations by random chance. And it's actually going to look like that histogram. Great job, Michelle, right there. Run a loop. And Sam also. For loop. Jesse also, right. So, no, it's just practice. So I tell you this much. Let me tell you, if you want to feel good about yourself, the first semester I taught 320, I never did it without the notes next to me. And sometimes I'd write code and it wouldn't work. And I still do that in classes sometimes. And I would have to say to students, oh, I'll email you this or something, because it just wouldn't work. I had students who I felt were better coders than me. And this is, my gosh, like almost 8-9 years ago now. But I was really afraid. So don't be afraid. Coding's about making mistakes. Coding's about practice. It's about, you're going to make a mistake. The code's going to break. It's not going to work. And just the more you practice, the easier it gets. And just don't be afraid. Just be like, oh, it doesn't work. And they'll be like, oh, let's figure it out. Does anyone else, we'll go back to the Kahoot right here. If when you are solving coding problems and you get a problem fixed, who else gets that moment of zen where it's like, yes, it worked? Like when your code works. That's one of the best feelings I get when like my code is broken and then I fix it and I'm like, yes, code working again. It's like I beat a video game to me. Exactly. Brandon knows what I'm talking about right there. So I love it. And when you get what you want or you make a really cool graphic, like I'm more about making graphics these days, but getting code working is just such a cool experience. Like, yes, it works. It's not broken anymore. But right there, great job. And dynamic orcs in the lead. Let's continue on. Here we go. True or false? Correlation implies causation. 201, you got this. Where's my 201ers at? Correlation implies causation. One of the easy questions we got right here. Won't spend too long on this one right here. Correlation implies causation. You got this. Think about Nicolas Cage right here. Not the bees. Nope. Correlation is never causation. We cannot say correlation shows causation. Not the bees. We're going to jump into the next question, so get ready. A little bit of an easier one right there. Dynamic orcs in the lead. Coding assignments dictated my motions more than... Well, next question. Here we go. The model used the starting point to compute the total sums of squared error is the... Ooh, I love this question. The total sums of squared error is computed from the what model? The starting point, the no knowledge model, the John Snow model. That was a quick next question. The John Snow model. The no knowledge model. It does it via the mean. The no knowledge model is the what model? The naive. The naive. So the naive model right here, when you think about the naive model, how does the naive model do its computations? How does the naive model do its computations? If we have a height weight model, or let's just go to plot height weight. So the naive model uses what to do its computations? The naive model uses what to do its computation? Who knows what the naive model uses? Well, I don't want to type it yet. You'll see the answer. It has no x's. That is correct. So I guess it'd be hard to do. I don't know if I could do it with no x's. It uses the mean of the what? You are correct. It uses the mean, but it doesn't use any x's, right? So if we're going to use the mean, and we are doing the mean to predict someone's height, when then we use the mean of someone's height. Oh, I need to do h equals. There we go. And there we go. This is the naive model. Great. No, Sam, great answer right there. And Kayla, great answer. The naive model uses the mean of the y variable. So when you think about this, we don't care what someone's weight is. We're just going to predict what? Everybody what? Tell me, I want you to predict Brian's height. Go ahead, use the naive to predict Brian's height. That's correct, Jesse. The naive uses the mean of the y variable. Predict Brian's height. Go ahead, chat. Use the mean, and you can see how it works. Don't worry about what I'm blocking, and look at the answer on the screen. 510. Use the model. Predict Brian's height. Predict Brian's height in inches. Use the model. Use the information on the screen to predict. 67 inches. I'll take that. That's close enough right there. 5'7". So predict my brother's height. 5'7". Predict Chelsea's height. Might be closer to our zone. Predict Chelsea's height. What do you notice the mean does, or the model does for everybody? Everybody what? Like, don't worry about height down here on the bottom, or weight, excuse me. What does the naive model do? The naive model does the what prediction for everybody. What does the naive model exactly, Ella, right there? It's going to make the same prediction. And it's not using an X variable, so it's not taking information from the X's. We just plot the X because we actually need to make some sort of plot. I guess technically, could I do this? Let's find out. Ooh, no, it doesn't like it. I just have to put in an X so we can see it, but I'm not using the X variable. Everyone has the same height. The naive is just like, well, here's the average height. Everyone's the average height. Who would like, if I told you, maybe, I don't know, if you're here, you might not like it. Who would like right now, if we made a deal and said, let's use the naive model for the test? Who would like that? Now, you got to watch out because maybe then that would influence people to change directions. If I said we're going to use the naive model for test scores once we know test scores, and we'll just use the naive model to give everyone their test score. So we use the naive model for test scores. Who would like that? To be like, I could look at how long you studied and your grade. I wouldn't right there. No thanks. Because now, and some people, if you're not here, they might like it. So sorry if people are not here. If you're watching this, congratulations. You probably will like it too. What am I telling you would get? And Jesse's saying right there, if I do bad, let's do it. Thomas wants it conditional on how they do. Understanding, Thomas, another 100 points, that the naive model would be the mean for all the data. It could just save you the stress. Be like, well, I'll just take the mean. But then you're getting the mean of what everyone else got. So you got to be like, oh, I hope everyone else does all right. Was everyone else studying? You don't have that much influence on it anymore. So if you do poorly, it's like, whatever. But yeah. Oh, Brendan, shout outs to Brendan right there. Thank you, Brendan. Brendan, that's worth some 500 points. Giving some props to the class right there. That's such a nice thing to say. I agree. I think the class is pretty smart. So yeah, let's take that mean model right here. Melodic Mouse jumping up into the lead right here. Continuing on. Oof, they got a lead, but you never know. Next question. Here we go. Which of the following is not a condition for regression? Let's find out. You got this. What are our conditions? Which of these is not a condition for regression? I think I have some output. We'll take a look at it here in a moment. We'll do one of these next. Which is, I agree, Brendan. Thank you so much. All that positivity. We love positivity here. Which of the following is not a condition? I mean, you want to collect your data this way. We do love this in our class, but randomness. We collect data randomly, but we have QQ straight up, no outliers. Let's take a look at them here in the output. We still have our models saved, and did I delete all my output? I don't know what I've done. Oh, it's on the previous page? Here we go. That's what I was doing on that. Okay. So let's go right here to Eagle Sprite. Of course, you bet. Let's go to check regression. And let's take a look. Oh. Model not found. Sad day.
Little bits.
Wrong button. Let's make our model right here. Height. Weight. Data. Survey 10. There we go. Okay. Tell me in the chat. Does this model pass or fail the conditions? Does this model right here pass or fail the conditions? Does this model pass or fail the conditions? Quick and easy thing we should know. So tell me if you don't understand, but does this model pass or fail the conditions? Your thoughts. This model right there, those p-values, they fail all of them. When it comes to p-values for assumptions, we assume things are good, and then if the p-values are low, we fail the assumptions. So this is failure, failure. Can anyone take this out of scientific notation for me? I know what it is. I don't want to say, but I want you to take it out of scientific notation, not be like, oh, it's 9. No, it's not 9. What is that in scientific notation or out of scientific notation? Just to make sure you know what it is. I'll type it in the chat, or can someone type it for 100 points? Tell me what that is not in scientific notation. So you should be like, oh, that's a pretty small p-value. But all of these are fail, fail, fail. Great job right there, Sierra, 100 points. Brendan, oh, you reversed the 9 and the 4, I think, right? Oh, is it? No, Sierra got it right there. Sierra got it, I believe. And then Paxton also. If you count the leading 0, you can count the amount of zeros. If you count the leading 0. So I used to get it confused. I'm better with decimals. I'm always bad when I have to go to big ones. I still get those reversed sometimes, or mistake on it. Brendan, don't worry, 100 points, practice. That's what we're here to do. Although we get it right answers for wrong and right points, wrong and right questions. So now what we have to do is we have to look at these plots. Now, the biggest issue I see in this one is going to be an issue where I see two big issues. So where do you see maybe the biggest issues? Where do you see the biggest issues? I'm going to try to trick you. You ready? Is the linearity good? Oh, great job, Kale is saying we got a big enough sample size. I should have mentioned that. Great job, Kale. Another 100 points. Chart 1 and chart 3. And those are the ones we look at. QQ plot is rough. Does the linearity look... No, don't talk about linearity here. This is normality of residuals. Remember, it says it right below. So I'm trying to trick you. And we see an issue down here. That might be a no-go. That might be like, this is really bad and we don't want to use it. And then the linearity is right here. Do not forget that this is the linearity. And then there was a question on equal spread before. Equal spread, I'll draw it visually on here. The way to check the equal spread of this is you would only look at this plot, and the equal spread would be checked by looking at the following to see if it's about equally spread. There does look to be, for the most, majority of the data, maybe there's an outlier issue, but there's maybe some thinning out of the data, maybe a little bit of outliers. This one, it's hard to tell the equal spread. It's not good, but some of them are more symptomatic of equal spread problems. But it looks to be thinning out a little bit. And we'd also see that in the original plot. We should see a thinning out later in the model. And do you see the thinning out over here behind my head? Who notices, yes or no in the chat? You've got a little bit of the outliers thing I was talking about. This is just a residual plot here. So you're seeing the outliers I shaded in yellow down there. And then you're seeing the thinning out over here. That's where the thinning out occurs, where we're maybe seeing less spread. Then you also see down here the outliers I was talking about here in the yellow. So are there outliers? There's probably some outliers. Is there some sort of small amount of non-equal spread? It is getting a little bit thinner, it looks like. So this regression has problems. It's not a happy regression today. It's a little sad regression. It's not a good time. But great work right there. Continuing on. Here we are. These are... Exactly. That's the thing. Brendan right there, another 100 points. It's like, is it good, bad? It's kind of... Real data is not perfect. Real data is weird. It just doesn't have clear answers sometimes. It's like, yeah, it's kind of bad. I don't know. How good's R squared? Jolly Owl jumping up to second place. Dynamic Orcs, though, doing a great job. Here we are at the next question. Let's do it. True or false? Residuals should be independent of each other. Here's a hint. And it kind of means the same thing. Should residuals be independent? Meaning that one residual would not impact another. What do you think? Independent is just a proxy for the word of random, basically. They're a little bit different, slightly. But if we're saying that they're independent, we want them to be random. So we don't want the residuals to have relationships. What is a good, if you know 201, we've talked about it a lot, a good residual plot should look like what? Let me ask you, is this a good residual plot, yes or no? Would this be a good residual plot for you? You got this, Kayla. Is this a good residual plot, yes or no? What do you think, yes or no? Is that a good residual plot? Your thoughts? We're pretending it's a residual plot. Is that a good residual plot? What would your thoughts be? Is that a good residual plot? What would you think? Someone said, here's my residual plot. Would you say, oh, no? Or would you say, oh, wow? Yes. No, don't worry. Yes, yes. Why? Residual plots is like what's left over. And think about like this. If you make dinner, what do you want left over? You want nothing left over. A residual plot should look very what? A residual plot should look very what? Because you don't want any variation left unexplained. Oh, no worries. This is the practice. We got this. So a residual plot should look very random. It should just be randomness. And they're like, oh, there's nothing to see here. Nothing at all. We won't play. No, that means that when we're done with this model, we want to be done with it. Does that make sense, Kayla? It's like, I'm trying to like make the analogy work now. It's like if we make dinner, then we want to use everything we make and not have anything left over. And this is like nothing's left over. We've explained everything right here. So hopefully that works for that analogy. But we don't want anything left over. We want to be like, okay, we've explained everything there is to explain. And we actually, like I'm trying to think of a really great model. Agree to disagree. Sometimes you get good models, sometimes you get bad models, and this would be a great residual plot. Very bad residual plots are going to show like change in linearity, change in spread, and then we have leftover things we don't want that we didn't encapsulate with our model. So yeah, we don't want that. We want a random residual plot. They should be independent. So high residual means when you say high residual, residuals can be high. You don't want them to be really high. You want them to just be random. Can you explain, Brendan, on that a little bit further? So high residual means likely random. Are you talking about the p-value? The p-values over here are good. We want them to be high because that means what we're seeing, the condition, our results were likely given the condition is true. So given like, let me try and make one. It's so hard to find things that meet oh, I think I know one that makes it. Let me make a good residual plot. Cross your fingers on this. Let me do HP by weight. Okay, let's try this on empty cars. And we're trying to make a good residual plot. Okay, what issue do you think there's going to be? What issue do you think there's going to be on this? Exactly, and that would be the linearity right there. Jesse mentions linearity. No worries, Brendan. I think this will help with this. I think I see an issue with this. We'll do the test on it. If we fail a condition, I'm guessing it's going to be what condition? If we fail a condition, it's going to be what? Well, kind of outliers. Oh, that could do it too. There might be two, Brendan. What two things, which you can see right here, the three conditions. What of the three conditions might we fail right now? What of the three conditions might we fail? What of the three conditions might we fail? We might pass linearity, or it might not even run it because we might not have enough replicates. It has to have repeat values of your x's to run. We're probably gonna, I think, equal spread and maybe normality of residuals. Let's see what it does. Normality of residuals is the only one we failed, and look at that. And actually, who said it? It was outliers. Brendan said outliers. Brendan, it's the outliers creating that issue. So the only issue with this plot is those outliers Brendan was seeing. That's not so much, it's saying it's not really an equal spread problem. The equal spread is good. The problem here is the normality of the residuals, and that's due to those high outliers. So Brendan, this would show that there's a problem with this model due to the extreme outliers. If you notice right here, here's the points, just in a different kind of format. And then here's them on the normality plot. So there's a big problem up here. And I might even say, there's such big outliers on this model. The model comes back saying it's a big problem. I might not use this regression. I might toss it out, even if, and we should do some summary of regression here too. We need to review that. We'll do that here in a moment because I think we have questions coming up right here. Ooh, we need to do interpretations. So hang on, stay tuned. Continuing on, let's do the next question. Melodic mouse and bold mouse. We got mouses and owls. They're like mortal enemies, and who knows who's going to win. Next question coming right up. Here we go. What is the uncertainty of the slope? You should know this very quickly in the output. Funny enough, a lot of output on the screen now. You have to find the uncertainty of the slope. This is the summary output. So what is the uncertainty of the slope? When you hear uncertainty, what word should you be thinking? When you hear uncertainty, what word should you be thinking? If you hear uncertainty, you should think, what word? The uncertainty of the slope is the what of the slope? Good answers. Great job. And Brendan, you're basically right. The uncertainty of the slope is the, oh no, that's all right. Did you get right, Kayla? Wrong? The uncertainty of the slope is the standard error of the slope. Just think of this: uncertainty in the intercept estimate, uncertainty in the diameter estimate, and then this, the residual standard error. Oh, you got it, Kayla. Nice job. The residual standard error is the uncertainty in the residuals. So that's typical miss the model makes, the residual standard error. So great work right there. Good practice. And we will, don't look at that. We will be going back over more of these questions here in just a little bit, or more of the output. So this is the uncertainty in the estimate of the slope, and that would be the answer. Great work. Who's in the lead? We're going to get to some interpretations here coming up. So I think I have them written out, maybe. Next question, here we go. What is the typical miss the model makes? We should know this instantaneously in our output. We just kind of mentioned it. This is, can you find the things in the output the typical miss the model makes, also known as the root mean squared error. So this is the root mean squared error. I don't want to say the other name for it, yes, because that's what is in the output. Or the typical miss the model makes. So what is this? The typical miss the model makes. It is the residual standard error. The residual standard error right here is the root mean squared error, and that is the typical miss the model makes. A classic thing we'd like to mention right here is when we're talking about residual standard error, nice job. Because how can you, if you know it's RMSE, when you know it's root mean squared error, what could you do right here just to remember it's like typical miss or average error? Mathematically, what do you know about this? And we do this because the residuals are positive and negative, and we have to square them to not have a zero residual, or else we'd have a mean error of 0. And exactly, cut out the root and the square, and we have to square it because they're positive and negative. So if we found mean error would just be 0. Without doing this, it would always be 0. So we have to square it, and then we root it to bring it back. You can also do mean absolute error. Some people are a fan of MAE. I'm not. Or mean absolute percent error. So many ways to do it. They cancel out, and we basically just get mean error. So it is called in the output residual standard error, but it is the root mean squared error. Just a lot of names for things. Continuing on, next question. Leaderboard's locking up, but it's a close game. Anyone could win right here. Next question. Here we go. Quiz question. What percent of the variation in Y is explained by the variation in X? Good 201 review right here. What percent of the variation in Y is explained by the variation in X? Blank percent of the variation in Y is explained by the variation in X. What do you see right here? Ah, they're so close. I can't confuse you on it. We'll see. I hope we have 100% right on this. We'll find out. What percent of the variation in Y is explained by the variation in X? We are definitely looking at what value right here. And we've only talked about one of these. It does say multiple in front of it, so that gives away the answer. But we're talking about the R squared. The R squared. So 77%. You tried. I didn't trick you though, hopefully, right? 77% of the variation in the meat weight of an abalone is explained by the variation in the diameter of an abalone. So blank percent of the variation in Y is explained by the variation in X. So please, in this moment, what do you need to make sure you have? Oh my gosh. What do you need to have? Like, what should you have and start working on and be creating? What should you be working on and be creating? Make sure you have these. What should you be working on and be creating? We want to make sure we have these, we get these going, and we're like, okay, we are going to create this. We're going to have this. Like day of test comes around, we got our cheat sheet ready to go. We got that cheat sheet front, back. We're ready to go. Great job, Nicole, right there. Make sure to have your cheat sheet. Only if you're in tool 1, you don't get cheat sheet. I'm sorry. But this helps with things like interpretations. Once you have your interpretations down and you have them on your cheat sheet and you practice, be like, okay, Brian's saying I'm getting full points for these. Snapshot this now. Great job. We're going to do some slope and intercept interpretation coming up here soon. But make sure to know how to interpret these things because I see some pretty interesting interpretations on the test. And I'm like, no, you have a cheat sheet. Oh, that's all right, Nicole. I'm like, no, use the cheat sheet. Write down. Like, no, I'll see very interesting interpretations of slopes. It makes me very sad. Continuing on right here to the next question. Let's do it. Zany Bat coming up there on the leaderboard. Next question. Here we go. Which is the correct interpretation of the slope? Love it. Love it. What do we see right here? Oh, I'm not going to say anything. I know it's not the full interpretation, but we'll do this here in a moment. Words are hard. Sounds like a Will Ferrell quote. It might actually be from like old school or something. Who notices this right here? Oh, please. Oh, please. I can't appear on the screen or I'll block an answer. Oh, no. No. It's all right. What is this interpretation from? What is that interpretation from right there? This is the number one way to lose points on the test. What is that interpretation in yellow from? Just take it, Dumbledore it out of your head. Toss it away. Stat tool 1 right there. Say, well, why'd you teach us that? I say, I'm sorry. From stat tool 1, we need to say 2 abalones, which that's the animal we're talking about. It's an abalone, it's a sea creature. And how would we interpret this? So take a moment. We're gonna throw out 500 points. I want everyone to take a moment right here and try to interpret this coefficient. Take a moment and interpret it. So we have here X is diameter. We're predicting meat weight. It's diameter in inches, and meat weight is in pounds of meat we get from this creature. We'll say it's pounds. I don't even say it's ounces. I don't know. It's pounds. So how would we interpret this? There's the start of it. How would we interpret it? And we'll write the blank interpretation here in a moment. How would we do it? Give it a shot. 500 points on the line. How would we interpret this? 2 abalones that differ in their what? So it's 2 abalones that differ in their X by 1 unit are expected to differ in their Y by blank units, where the one with a higher blank is expected to have a blank or blank. 2 abalones that differ in their diameter by 1 are expected to, on average, to differ in their weight by point. Oh, wrong coefficient right there. Check the coefficient. Ella, great work. Throwing another 100 points, Ella. Good start right there. The point. Oh, you grabbed the standard error, Ella. You have the standard error. You want to use the estimate. The standard error is just the uncertainty in that. You want the estimate right there. 2 abalones that differ in their diameter are predicted to differ in their meat weight by 1.9 units on average. And then finish it off with where the abalone that is bigger is expected to get more meat weight. And that's got it. Let's throw out 500 points. People are practicing right here. But make sure to add that last sentence where we say where the abalone that is bigger is expected to have more meat on it. And remember, we're talking about this coefficient right here. That is the estimate of the slope. So 2 abalones that differ in their diameter by 1 pound are expected to differ in their meat weight right there, by 1.09, where the abalone with a bigger diameter is expected to have a higher, and then meat weight for the Y variable, Kayla, right there. So make sure to, I'm going to copy paste it and just change the second diameter to meat weight. And then the next one would be... Does that make sense right there, Kayla? No worries. This is practice. This is why we're here. Imagine day of tests. We get all the practice. This is just practice. You're going to have to type it out during the day of the test. So this is great practice. Like, even if you rewatch this and you're like, let me try practicing it. Let's do the other one over here where we're trying to interpret the horsepower of a car and we're using weight. Who can do this right here? Weights we'll say is in, weight is in tons and horsepower is in horses. So who can interpret this one right here? We're predicting the horsepower of a car from the weight of a car. So who can interpret the regression coefficient right here? We're trying to interpret that value. So that is the slope coefficient right there. That is the estimate of the slope. So take a moment right here and we're saying 2 watts that differ in their X by 1 unit are expected to differ in their Y by B1 units, where on average, where the one with a higher X is expected to have a blanker Y. So take a moment right here. One more try at this. You got this. Second try is a charm. Interpret this slope. For the output. So people say, good practice right here. Good way to make sure you're ready for the test is to be like, can I write these interpretations? So what do you think? I can say it, but it's better if we practice it. 2 cars that differ in their weight by 1 ton are expected to differ in their horsepower by 46.16 horsepower. On average, with the car with the higher weight expected to have the higher horsepower. Great job, Nicole. That's another 500 points. Nicole, just right out from the start right there. Nicole, I'd look at that and I'd be like, yep, boom. I'd be like, 12 points on that. And then we have other great answers right here. Let's take a look. 2 cars that differ in their weight by, it'd be like tons or something. The question will state it, Sam. 2 cars that differ in their weight by 1 ton are expected to differ in their horsepower by 46 horses. I do like that. Where the car with more weights, which have higher horsepower. 2 cars that differ in their horsepower by 1 ton, because we should give context, are expected in their horsepower by, and then by their horsepower by 46, because that'll be the units of the Y. The car with the car, and then watch out, Wills. Remember, never mention our friend Will right here. Do we have that command in the chat? So remember, not to mention Will. We say expected or predicted. We don't want to say will because that sounds cause and effect. Two cars that differ in their weight by 1 ton are expected to differ in their horsepower by 46.166 units. Where the heavier car is expected that, and I would take the expected there on the second. Brendan, great answer right there. Kayla says two cars at different horsepower by 1 unit are expected to differ in weight by 46.1 with the car with the higher. Yeah, no, Kayla, I think that works. Wait. No, by 46. Yeah, then the units, the Y should be horsepower. Does that make sense, Kayla? And Kayla noticed that there at the end. Two cars that differ in their weight by 1 ton are expected to differ horsepower by 46.16 horsepower, with the car with the larger weight is expected to have a higher horsepower. Since you already said expecting, you didn't say will, I'd probably be okay with that. Yeah, it has the higher predicted horsepower. No, good work right there. Let's write down our blanket interpretation of these. So 2 blanks that differ in X by 1 unit are expected to differ in Y by B1 units, where the one with the higher blank X is expected to have a higher / lower Y. So make sure to do context. This is so key. You need to make sure to put in your units and your X and Y variable, and it becomes easier with practice. Like, who the first time you wrote this thought this was like impossible to remember or write, and now it's becoming a lot easier. I hope this is becoming a lot easier to say, like, oh, 2 cars that differ in their weight by 1 ton. Well, we expect them to differ in their horsepower by 46 units of horsepower, where the car that, weighs more is expected to have higher horsepower. We're just saying, generally saying that cars that weigh more, we predict them to have higher horsepower. And that's what you want to get in the theme of practicing, is being able to say it like 2 cars that differ in their weight by 1 ton are expected to differ in their horsepower by 46 units of horsepower, where the car that weighs more is expected to have higher horsepower. And just practice it. Make sure to know it. Make sure to have this written down. Exactly. This is why we're so picky, is because it's like we don't want to say will, because that implies cause and effect. And then we're just saying what we observe, generally speaking, that the model shows predictions. And this is why we're so picky, is because the model is making predictions about what we would expect if a car differs in its weight by 1 ton. We'll assume it's ton right here. So let's words of pledge. Oh, man. I think I still know the pledge. I think I do. I might not. I don't know what's happened to me. I got old is what happened. Cheat sheet. Oh, Kayla, I'm throwing 500 points. Kayla said it so perfectly. No need to memorize. Cheat sheet. Put it on that cheat sheet. Make sure to plug in, identify your X, identify your Y. Be careful. Double check it, triple check it, and get those points. Next answer. Oh my gosh. Leaderboard shakeup. Who's going to win? Let's find out. What is the margin of error for the diameter estimate? Oh, this is such a tough question. There's the diameter. What is the margin of error? You can look at it and see it pretty quickly. What is the margin of error for the diameter estimate? It goes from 1.06 to 1.12. This is a good, tough, quick question. What is the margin of error for the diameter estimate? What is the margin of error for the diameter estimate? That is a tougher question. And a lot of people didn't get the margin of error. But what is the margin of error? Like, I want you to define what a margin of error is for me. A margin of error is what? Margin of error. A margin of error is a what? What is a margin of error? If I tell you that a candy bar, I've done a lot of research on them, and a candy bar costs about 106 to 112. John said it perfectly. A margin of error is half the length of the interval. So the margin of error right here is plus or minus. So margin of error can always be written as plus or minus. And the margin of error is going to be half the length of the interval. And, oh, that's all right, Kayla. Don't worry. You're probably doing great. You might be in the lead. You might be number 1. But the margin of error is always half the length of the interval. Half the length of the interval. What was the estimate of meat weight? Who knows what if I rerun this model right here, who knows what can anyone tell me the estimate of meat weight? Like, are we using diameter? I think diameter is the variable. Who knows what the estimate was? Using this interval here, you can tell me the estimate. Who knows what the estimate of the coefficient of diameter is? the estimate for the coefficient of diameter is what? I'm about to do a complex series of questions. 1.09, because the estimate is at the center of the interval, because you're saying, I think it could be as high as this or as low as this. And then we're saying, well, the estimate's at the center and it builds the interval. Now I want you to look at this. This is a 95% confidence interval. And I'll throw 500 points if anyone gets this, because we should know it, but it's a tougher question. Who knows what the standard error is of this interval? Who knows what the standard error is of this estimate that would create the interval? Who knows what the standard error is? And I'm speaking specifically about these values right here. We know the estimate is 109 because it's at the center. You just average the two values, 106 and 112. Close, Jesse, close. That's the margin of error because that's half the length of the interval. But if I do a drawing, I think the drawing will help us know the answer. If I go here and I go to Microsoft Word and I do the following, let's see, you ready? Watch this, you ready? What if I draw this for you? If 109 is at the center, and I'm telling you that this is a 95% confidence interval, Ella, we'll throw out those points. Ella got it. Because Ella, what are you doing? Ella's figured it out. Because Ella's confirmed, and I'm not doing it prospectively, right? That should be right about there. That's good. Ella, explain the chat. And Ella, we're going to bump it to 1,000 points. That was a really tough question. That's one of the toughest questions I can ask. And Ella might be typing an answer right here as I explain it visually. Good answer right there, Ella. That is correct. It is half the margin of error because a 95% confidence interval goes out 2 z-scores plus and goes down 2 z-scores minus. And so if your margin of error is this is the margin of error of the interval. And then you could cut that in half to get half the margin of error. So we know the margin of error is 0.03 and 0.03, and this was then 112, and this was then 106, making the interval to give the estimate. That's not where it's at. It goes here. And now right here, this would be 1.075, and this is the length of a standard error. So that right there. No, this is some of the toughest questions we could ask. Like solving a value and knowing how it's calculated. It's a very, very theoretical question. It's a good thing to understand. But the standard error is a measure of uncertainty. And I think, let me show the data right here that created this. So we need to go to the abalone data set. I try to put some pretty tough questions on here to go into some pretty complex things. Let me go grab the data. And it is called meet.weight. And we're using diameter, meet.weight, diameter, and data equals ex4, x3 abalone. And take a look. And Ella said it right there. There's the value Ella predicted it to be, about 0.015. Now, here's the thing to remember. If we made a 68% confidence interval, and this is where your Stat 1 knowledge comes into play, can anyone tell me the upper bound on a 68% confidence interval? Who knows the upper bound on a 68% confidence interval? So just pause for a moment and be like, okay, so we take our estimate and we do what to make a 68%? We do have questions on the test like this. Who could tell me the upper bound for a 68% confidence interval? What would the upper bound be? And I was showing it just a second ago, just about. So you would go to your estimate and you would do what? So you would say, well, I think it's about 109, but then the upper bound of the interval. So when we estimate what something will be, we have an estimate of what it will be, right? And then we have our measure of uncertainty. The uncertainty creates the interval around the estimate. The uncertainty creates an interval that would say, what is the truth contained within? So when you hear 68, what z-score do you think of? And we'll go back to the graphic right here and show it. When you hear 68, what z-score? And Jesse, 100 points. Thank you for excellent tries right there. When you hear 1, right? So what do you think the upper bound would be? What do you kind of predict the upper bound to be? Like using this graphic right here, using the information on the screen, the upper bound would be about what? Of a 68% confidence interval, the upper bound would be close to what? And I don't have the answer on the screen. It's the only thing missing. The upper bound would be about what? Very close, John. Change the decimal. Is that right? Is my math correct right there on that? That should be it right there, right? 1.105. Because what am I doing? I'm going up and down what? To make a 68% confidence interval, I'm going up and down what? So when you think about a 68% confidence interval, I'm just going up and down what? For a 68% confidence interval, I'm just going from the estimate, I'm going what? Does that make sense? To make a 68% confidence interval, I'm just going up and down what? One and standard error technically. These are standard errors technically. But I'm going up and down one standard error. So now we're going to have the output tell us the exact answer. And look, didn't we just say that? 1.105. That's what we wrote. We wrote 1.105 on the sheet, 1.105, and we wrote 1.075. And there's the answer, 1.075. Now tell me this. If a 95% confidence interval is this, where do you think a 99.73 technically? Well, so think about this scale right here. Think about the z-scores and how they work. If we were to make a 99.7.3, that's the technical, probably fine to put that, 99.7, then, so with this one right here, this one might help, and I hope there's a light bulb moment. We'll see if there is, and we'll review. These are the tougher questions, like I said, hence why the big points. What would be the lower bound on this interval? Just think about the way it's working mathematically right here. With 68, 95, what would be the lower bound on the next interval? When you go 68, 95, well, that's the interval we're currently on. The next interval of 99.7 would have a lower bound of what? The 99.7 would have an interval of what? If you go 68, 95, 99.7, the lower bound, very close, Kayla. You rounded it probably, but that's very close. So how much further down are you going to... That's very close. And so you're just going down one more standard error. Does that make sense? Like visually speaking, we'll show the visual here and then we'll show the mathematics behind it. Visually speaking, you would just go out one more standard error. And so I'll do the upper bound and I'll let you tell me the lower bound. But there's 3 standard deviations up. There's 3 standard errors technically. Great job, Paxton. You're seeing it. Yep. It's one of those things when you see it, you're like, oh, that's how it works. And Paxton said 1.045. So you're just going up and down more standard errors. Like you're covering more of the curve by doing more uncertainties out from it. And so when we run this right here, we'll probably get a number pretty close to that. And there it is right there. That's the number Paxton just told us, the 1.045. And so it does this for us. It makes a confidence interval to estimate. Now, I do want to mention an easier thing to remember. Is everyone ready for an easy thing? Who's ready? I'm raising the chat for an easy thing right now. Who's ready for an easy teaching to the test moment? I think this is on the test. I think I've seen it most of the time. This is an easier thing. Let's see if anyone's ready. This is an easier concept. You ready for an easy one? Right here, right here, right. Got this, got this. You ready? Why is this interval statistically significant? Now be careful. This is a p-value to estimate the slope of a line. Why is this result right here statistically significant? Why is that interval estimating the true slope of the model statistically significant? Explain to me like, oh, well, that interval estimating the slope, boom, Ella got it right there. It does not contain 0 because a slope of 0 is the naive model, and we care about whether or not the slope is 0. So it is statistically significant, and we see that also here. Both are statistically significant, but we care about the slope of the line. It does not pass through 0 exactly, which would be the naive model. So this model is statistically significant because we do not see a possibility of a 0 slope. So we do think there is evidence of statistical significance. So that's a really good thing when we do the confidence intervals for the estimates in a model. Excellent work. That might be one of the upcoming questions. Who's in the lead? Shake up on the leaderboard. No. Oh, top 3. 2, 3, 4 did not get points. Clever pony, you never know. Let's see who's going to win. Get ready, get ready. Here we go. 3 more questions to go. The intercept can have no meaningful interpretation. True or false? The intercept can have no meaningful interpretation. Great job, Gia, right there. This is good practice. And thank you so much, everyone who showed up tonight. Got a few people watching live. Love it. And people can use to review later. But we've done a lot of stuff to review right here. Good practice. And the answer is yes, the intercept can have no meaningful interpretation. What we mean by this is sometimes it's illogical. think about this right here. We did a car data set, right? How would we interpret the intercept of this model? How would you interpret this intercept? Pretend you have to interpret this. Your whole test grade rests on you interpreting the intercept. So you might want to add that it's not logical afterwards. We'll write down this final interpretation, but interpret this interval. Great job, Gia and Kayla and everyone. How would we interpret this interval or the intercept? Which is doubly not possible. I'll put down some notes here while you think about it. You need to see the value though, so I'll go over here. There we go. Let's see. There's no Sam, I might have to accept that. Sam's answer, 100 points right there. I'd look at that and I'd say, how do I grade this? It's a pretty good theoretical answer. So we'd say when x is equal to 0, we expect y to be b0. A lot of people forget the is this logical part. So with a, oh, did you do the diameter? Oh, this one is the weight. This one's predicting weight. So we'll take a moment right here. This one is the weight of a car. So let's see right here. And then is this logical? You might want to add that on at the end. So we got a few answers. Let's see. So with a, so it wouldn't be diameter. This would be with a weight. We switched to the example right here. This one is weight of a car predicting the horsepower of a car. I went back to the first one. Because, well, yeah, the other one wouldn't make sense either. I should have just done that, Eller. I should just kept with the current example. So how would this be? Good practice. Interpret the intercept. Who here can interpret this intercept and make it make sense? So we have to plug in our x variable. We have to plug in our y. So there's the x. There's the y. Then we have to plug in our b0 value. B0 is right there, excuse me. And is this logical? When weight is equal to 0, we expect the horsepower to be negative 1.821. We can't have negative horsepower on a car or weight of less than 0. Kayla, 100 points right there. Great work. That's exactly right. Exactly. That's what exactly we need with the horsepower of 0. Oh wait, with a weight of 0, John. With a weight of 0. So when weight is equal to 0, because that's the x. Good work there, John. Also, Samari, it's when x is equal to 0. When weight is the car of 0, we expect it to have a horsepower of negative 1.8. This doesn't make sense because you can't have negative horsepower and you can't have a weight of 0. So great work, Kayla. That's 100% right there. That's what we want to hear. I'll read Kayla's answer again. When the weight of a car is equal to 0, we expect the horsepower to be at negative 1.821. We can't have a negative horsepower or a car that has a weight of 0. That's it. That's it. That's great work. Few more questions to go and really good practice. Let's see who's going to win. Leaderboard shakeup. The mouses are back. Uh-oh, here we go. 2 more questions. How many tests are failed? Review question right here. Love it. How many tests are failed? Who knows? This is a great question. I'm trying to think. I think we wrote some of these on the test. If you know this output, you know how to answer this immediately. The null hypothesis, if you use null hypothesis, is that every test is passed and the p-values are low. The null would be test for linearity is good, test for equal spread is good, test for normality is good, and we fail all of them. And make sure to have this note down. When doing assumption tests, low p-values mean we what? So finish my sentence in the chat. Make sure to know this. When doing assumption tests, low p-values means we what those assumptions. When doing tests on assumptions, low p-values would mean we what? When doing a test on the assumptions, low p-values would mean we what? We would reject the assumption or fail the assumption. Correct, Jesse. Great work right there. We would reject the idea of normality. We reject the idea of equal spread. So this is, you can say it that way if you like. Now don't say except and don't say the bad except word. We would say I reject that this is linear. I reject that there's equal spread. I reject that there's normality. And all those ideas are preposterous here. We would not believe such a crazy thing. Who's ready? Oh, it's time. Here we go, everyone. Get hype for the last question of the night. More review coming up in class. More practice, so get ready. Here we go, last question. Who will win on the leaderboard? Dynamic Orcs is taken away right here, but we've still got possibilities for second, third, fourth, and fifth. Here we go. Last question tonight. After we fail a test, what is the next step? What is the next step right here after we fail a test? I think Kayla mentioned this earlier, and I'm going to cross my fingers I chose the right answer. The next step after failing a test, we did some practice on this earlier, is to do what?
It is.
Here we go. There's my real voice. Music. The next... No, don't cry. We check to see if there's a sample size greater than 25. My voice sounds all crazy today. Great work, everybody. Let's go over to the final leaderboard. Here we go. Oh, no, we don't have music. Brown music. Bald mouse. 15, that's good. Melodic mouse. The mouse is in the lead. And only one question missed. Dynamic Orcs. Great job, everybody. Excellent work. Tiny Brian out.
Oh my gosh. Great work, everybody. Woo! I'm going to go take a break. That was excellent work. Good practice. Did you come in third or second or first, Kayla? I know you said you had a streak, but I think it was after the first question. So Dynamic Orcs just led the way. So Kayla, second or third? Email me on both to be like, I won this and I won this, and we can double it up. Send Starbucks or send Amazon. Make sure to email me and say, hey, Brian, I came in this place and we got it. I'm sweating. Did you get it? Oh, you're sweating. Well, with that, I'm going to take a break and we're going to relax. I came in third. Nice job, Kayla. Kayla, great work. I think that's just so awesome. Like, it means a lot to me that people are... Can people not in your session attend class for more review? I guess they can. I guess. I mean, like, I guess. I mean, I'm okay with that. If I don't know. I'm not against it. If the link is out there somehow, I'm not against it. I don't purposely send it out. You came in third last semester. Make sure to email me if it's 10 for both, or if you know what it was for the last one, just let me know, and then I'll send both. Like, I'll double it up and send it. Yeah, no, like, if someone's in like watching and reviewing, I'm fine with that. But I'm just always there to like have some fun. I don't. Oh, that's. I feel bad because I don't know. I'm just like I just like it's hell, like if the link's out there, so I guess that's what I would say. I'm not against it. I'm not gonna like, does that make sense? Like, I'm not gonna like kick someone or be like, you can't be here, because I would just think about it like, if somebody were to be like attending, like, or walked in, it's no, like, I'm fine with it. Like, if people were like, when I teach in person, if someone's like, hey, I want to bring my like brother, or want to bring this person, or this person wants to show up, I'm like, yeah, sure, whatever. Like, if they want to come in and enjoy the class, that's fine with me. I don't know. I like the idea of, like, to me, education's always about, like, helping each other out. I think that's what's awesome, is like, we're here to help each other out. We're here to learn together. And that's what I appreciate. We will be back. I'm going to go grab some food. Everybody, we're going to be practicing more. Oh my God, it's Mewbots everywhere. How did I even do that? Mewbots. There's an army of Mewbots on the screen. Oh, scary. I'm just saying my husband is invested in stuff. Nice job right there. With that, we'll be back here tomorrow. Swing by class, enjoy, relax, and I'll see everyone then. Bye for now, everyone. Bye. Time for dinner. Enjoy dinner.